Hello everyone, I'm Dr. Rashid Hajij and this is summary for the lecture about complexity of algorithms. This is a very important topic in computer science, both from a practical and theoretical point of views. In practice, we want to know if our algorithms are efficient or not. In theory, people study complexity of algorithms in a very abstract way and try to relate different classes of complexities to each other. For us, we will focus more on the practical side of the topic and just scratch the surface in terms of theoretical concepts. The learning outcomes for this lecture are as follows. By the end of the lecture, you should be able to explain why the study of complexity is important. You should also be able to estimate the time complexity of your algorithms. You should also be able to determine the complexity class of an algorithm using the big O notation. And also, given a problem, you should be able to compare the complexity of different algorithms for this problem to select ultimately the best one. And by the end, you should be able to explain what is big omega notation, what is the big theta notation, and how they are related to the big O notation, and when to use each one of them. In the first part of this lecture, we're going to focus on the 2 points, explain why the study of complexity is important, and also estimate the time complexity of an algorithm. The first thing we're going to do here is to agree on the definition of an algorithm and what type of algorithms we will focus on in this lecture. Given a problem, an algorithm is the description of the process the computer needs to follow to solve it. Basically, it's a sequence of instructions. An algorithm can be written in any language as long as it conveys the idea about how to solve the problem. It could be written in a natural language like English, for instance, in pseudocode, or using a fully fledged programming language like C++, Java, Python, or whatever. People in general like to use pseudocode, which is in midway between natural languages and programming languages. When using pseudocode, you benefit from the ease of describing things using the natural language, and also you benefit from the structuring capabilities provided by programming languages. The type of algorithms we're going to deal with in this lecture is a very general one. It is the type that takes some input data, performs some processing on the input data, and then generates an output as a solution for the problem. As an example, let's look into this problem about finding the sum of the elements in an array of size n. Here we see an array of size 8, so n is equal to 8. And the way to find the sum of all the elements is very simple. You need just to define a variable. You call it sum. You set this variable to 0. Then you scan the array from the beginning until the end. And each time take the value you encounter and add it to the sum here. Once you have scanned all the values and added them to the sum, well, you will end up with the total inside the variable sum. This is the algorithm written in the 3 ways, in natural language, in pseudocode, and also in a programming language. In English, it says, first define a variable sum and set it to 0, exactly as we mentioned. Then add all the elements of the array one by one to the sum, a variable sum. At the end, return the value of sum. The pseudocode says exactly the same thing in a little bit more structured way, and the program in C++ says exactly the same. After writing an algorithm, we want in general to know if it is efficient or not, and to do so, we have to conduct a complexity analysis of the algorithm. But first, we need to understand what is the complexity of an algorithm. Well, it is just an estimation of how much resources does the algorithm require to find the solution for the problem. The type of resources we could be interested in are time. We want to know how long it takes to find the solution. It could be also memory, how much space does the algorithm require to find the solution. And also it could be other type of resources such as network bandwidth or maybe electricity consumption and many other type of resources. But it could also be a combination of all of these. In this lecture, we're going to be focusing more on time complexity. For iterative algorithms, only those which use loops. For recursive algorithms, we're going to be treating this in a different lecture. Well, when we focus on time complexity, we're going to be developing tools, and these tools could be used also for other types of resources. So the technique is very generic. Now, the complexity of an algorithm depends on the input for the algorithm, and more specifically on some parameters of the input, such as the size of the input data. These parameters are referred to as the size of the problem. If you remember, in the previous example, our algorithm was about finding the sum of the element of an array, and the time required by the algorithm would depend definitely on the size of the array, because you need to go through all the elements and add the elements. So the more elements you have, the longer it takes to add them. So in this case, the algorithm depends on the size of the array n, and therefore we say that n is the size of the problem. Now, why is it important to study the complexity of algorithms? Well, you need to understand that given a problem, it might have several solutions or algorithms to solve it. For instance, if you take the sorting problem, there are many algorithms which can solve the problem. There is insertion sort, selection sort, quick sort, and bubble sort, and maybe others. And given a solution algorithm to your problem you're interested in solving, well, you need to evaluate its complexity to see if your solution is efficient or not, or even if it is feasible or not. And also, we need to be able to compare the possible solutions and to see which one is the best one to use. To illustrate the importance of studying complexity, let's look into an example. The example is about the traveling salesman problem. This problem is very famous in graph theory and has many applications in several fields, such as circuit design, electronics, and many other problems like order picking problems in warehouses, vehicle routing, etc. Well, the problem is about a salesman who has a product he wants to sell in different cities and want to do it the most efficient way possible to save on time and fuel. For this, he needs to find the shortest possible tour that allows him to visit each city once and brings him back to the original city from where he started. Here we have the definition of the problem. So given n cities, city 1, city 2, etc., city n, and the distances between the different cities. So here dij is the distance between city I and city j. Find the shortest tour. Here we see an illustration of a network of cities, and we have roads between those cities with different lengths. A possible tour could be to start from A, then go to E, then go to F, then go to D, then go to C, then B, then come back to A. This is a tour. The length of this tour would be, take 8, you add it to 10, then add it to 12, then 15, then 14, then 9. And if you do the sum, you will get the length of the tour. Is it the only tour we have? No, there are many other tours. So when we start from A, we could have gone to F at the beginning instead of going to E. Then from F, we could have gone to E. Then from E, we could have gone to D, then C, then B, then come back to A. An alternative would be to start from B and do the same. Of course, we could have started also from C or from any other node. So as you can see, there are many tours. Now, a straightforward solution would be to enumerate all possible tours, compute the length of each one of them, and take the shortest one. The shortest one would be the solution for our problem. Now we need to see if our algorithm is efficient or not. We do this by evaluating its time complexity relative to the problem size. In our case, the problem size is the number of cities, n. So we want to know how much time the algorithm requires to find the solution for a network of n cities, and also how does this time grows when n grows. For this, we will count the number of operations the algorithm performs. When we get this number, we need just to multiply by the time each operation takes to execute to find the total time. For simplicity, in this exercise we'll count only additions, and therefore our complexity formula will be just an approximation of the real complexity. To count the number of additions, we need first to count the number of possible tours and multiply by the number of additions each tour requires to find its length. Now, given a network of n cities, how many different tours are there? This is a counting problem. To find the number of possible tours, we need just to count the number of choices we have to build a tour. For simplicity, we assume that the network of cities is fully connected. This means that there is a direct road that connects each pair of cities. To build a tour, first we need to choose the city to start from. We have n cities, so we have n choices for the first city. After that, we need to pick the next city to go to. Since we picked already one city, so what remains is n-1 cities for the second city. For the third city, we're going to be having n-2 choices. Why? Because we already picked two cities, the first one and the second one, and so forth. For the last city, we're going to end up with only one choice. Why? Because we already picked n-1 cities, and what remains is only one city to go to. We need also to understand that we need to go back to the original city we started from, and for this we're going to be having only one choice. So the number of tours is going to be n times n-1 times n-2 up to 1, and then of course we need to multiply by 1 to go back to the original city. And this number is just n factorial. The number of additions each tour requires is n-1. Why is that? Because a tour around n cities contains n roads. To find its length, we need to add n numbers, which are the lengths of the roads. And this requires n-1 additions. The total number of additions is going to be just the product of the number of additions for each tour times the number of tours. So the total complexity in terms of number of additions is going to be this formula here. Fn equals n-1 times n factorial. One last clarification. In the computation we have just performed, we assume that the network is fully connected. If this network was not fully connected, counting the number of tours becomes very complicated. Well, this is because each time we reach a city, the number of choices for the next city would not be constant. It would depend on what is the current city and also what are the cities which have already been visited. In the network we have used for illustration, some cities are not directly connected to each other, and therefore this is not a fully connected network. To make it fully connected, we need just to complete it with missing roads, like the road between A and C. And we set the length of this road to infinity, just to say that actually the road doesn't exist, or it has an infinite length. This way, any tour that contains a road with length infinity will be just discarded, since its length will be infinity. In addition, in our example, we assume that all roads are bidirectional and therefore have the same length in the forward and backward directions. In the general case, it could be that between two cities there is one way road in one direction and another one in the other direction with a different length. For instance, if you take city E and city D, it could be that there is one-way road with length, let's say 20, and in this direction, and another one-way road in the other direction with 12. So this is just to give you an idea about the general problem. In the general problem, we assume that the network is fully connected and the roads could be bidirectional. Now let's see if our algorithm is efficient or not. Let's assume we have a computer, a PC, that can perform 10 billion numerical operations per second. We talk about floating point operations. And if this is the case, the time each operation takes to execute would be just 0.1 nanoseconds, which is pretty fast by today's standard. Now let's take different problem sizes and see how long it will take to find the solution. If we take n equals 8 cities, knowing that the number of additions is n-1 times n factorial, n-1 times n factorial. We get 7 times 8 factorial, which gives us this number here. Considering that each addition takes 0.1 nanoseconds, the time will be roughly 30 microseconds, which is pretty fast. Now let's take 50 cities, which is not very big, by the way. The number of additions is 49 times 50 factorial, which gives 1.48 10 to the power 65. This is the number of additions required to find the solution. Well, this is a very big number. When we convert it into time by multiplying by the time each addition takes, which is 0.1 nanoseconds, we find this number of seconds. We convert it to minutes, we find this number, and so forth. We convert it into years, we find this number. We get 4.73 10 to the power 48 years. This time is huge. It's more than the lifetime of the universe, which has been estimated to be just 14 billion years. 14 billion years, 10 to the power 9 years. This means that if you start running your program on this computer, it will never finish, even if you run it on the fastest computer in the world. For someone who doesn't compute the complexity of this algorithm, as we did, might think that maybe the computer is not fast enough, or maybe there is a bug in his implementation. But the truth is that the complexity of the algorithm is the problem. It's very high complexity. Now, is this a good algorithm? Well, definitely it's not a good algorithm. Is there a better solutions? Well, there are some solutions which work pretty fast for special instances of the problem. For instance, if you take a network where all roads have length 1, well, here the solution is very straightforward. The best tour would have length n, and the number of additions required is going to be just n minus 1, which is pretty fast. Other solutions or other algorithms use heuristics and techniques to find the best solution, and they do in general pretty well at finding approximate solutions. But general efficient algorithm that works for all cases does not exist yet. No one has been able to find an efficient solution. The best that exists so far has an exponential worst case complexity. So it's in the order of 2 to the power n, multiplied by, if I remember, there is a solution which has complexity 2 to the power n times n to the power 2. And this, by the way, uses a technique based on dynamic programming. So if you can come up with an efficient solution for this problem, you will definitely be very famous. Why? Because the traveling salesman problem belongs to a class called NP-complete problems, or non-polynomial complete problems. In this class, there are many other problems, and they are all related to each other, in the sense that each one of them can be translated in the other one. So if you can solve one of these problems in the class NP-complete problem. Now, regarding space complexity, how much memory do we need to run our algorithm? Well, it depends on how do we manage our computations. If we compute first all tours, then we compare them to find the smallest one, this would require an amount of memory proportional to the number of tours, which is very high, as we have seen. But instead, what we can do, we can compute tours one by one, keeping the smallest one, and this would require just an amount of memory to store one tour, which is very small. So memory complexity for this problem is very small, whereas the time complexity is very high. Now we know that there are some problems which do not have good solutions at all, and if we don't conduct complexity analysis as we did for the salesman problem, we might get into troubles when we do the implementation. Just for completeness, you need to know that there are problems which do not have any solution at all. It's not like people did not try hard enough to find a solution. The fact is that there is no solution. It doesn't exist. One of those problems is the famous halting problem. The problem is writing a program, let's call it H. This program takes another program the source code of another program P and tells if this program P halts or not, means if it stops when it's run or if it loops forever when it is run. This problem has no general solution at all. Well, you can find and write a program that works for some special cases, but a general program that works for all possible inputs does not exist. The proof can be done in many ways, but we're going to be doing here a proof by contradiction, a simple one. The proof goes this way. Let's assume that the program HP exists and someone wrote it. Now what we can do, we can use this program to write another program. Let's call it A for absurd, and this program will do the following. If h of A equal true, means if the program A halts, what we do, then loop forever. And here to write a loop forever in C++, it could be just like while true. Else, stop or return stop. And here in C++, you can do it just by doing return. So what this program does, as you can see, it doesn't take any parameter, so it's going to be either stopping or not stopping. So it's not influenced by an input. And this program does the following. It calls the function h, or the program h, which is supposed to exist, and gives it as a parameter the program A itself, this program, the whole program, this program. It's given as a string to the program h. Now, since h exists, it will be able to tell us if this program A stops or not. So if the program A stops, then it will loop forever. But if the program A doesn't stop, well, it's going to stop. And here where the absurdity or the weirdness comes into existence. Since A is a program, as you can see, it's just a normal program. It either stops or doesn't stop. Now, if you assume that A stops, let's run it and see if it stops or not. So we assume A stops. You go inside if halt A, so halt will tell you it stops. And then what A does, it loops forever here. So if A stops, it will never stop. Now, if you assume that A doesn't stop, run it and see what's going to happen. So if it doesn't stop, when we come here, H will tell us it doesn't stop, so it returns false. Then what do? You go to the else. And what do? You stop. So if A doesn't stop, it stops. And if it stops, it doesn't stop. Well, this is a contradiction. And where does the contradiction come from? Well, it doesn't come from the fact that the program is not correct. No, the program is correct. It is a program. The problem comes from the fact that this function h doesn't exist. Because when you assume if it exists, you're going to be doing some weird things with it. Now, given an algorithm, how do we compute its complexity in a more systematic way? Well, if you remember, for the traveling salesman problem, we counted the number of operations a problem of size n requires and multiplied by the time each operation takes. For simplicity, we considered only additions to get an approximation about the execution time. Well, in reality, this is what people do, but they do not report about time. They report only about the number of operations. The problem with time is that it depends on the language you use to implement your algorithm and also on the computer you use to run it. If you change the language or the computer, the time will definitely change. What does not change is the number of operations. So, the number of operations is used as a measure of the complexity and abstract way from implementation details. Of course, the time will be just proportional to this number. But do we count all operations? No, we try to keep it simple. We ignore housekeeping. We ignore all operations which execute a constant amount of time. We count only expensive operations and only those operations which are related to the problem we are trying to solve. For instance, if you consider searching, well, it's about comparing numbers. So we use key comparison or number comparison. We count those operations. If it is a sorting problem, well, we count also number comparison. If it is a numerical algorithm, an algorithm which uses additions, multiplications, and so forth to do calculations, well, in this case, we count the number of floating point operations, flops, like division, multiplication, etc. And sometimes what people do to get a rough estimate of the complexity of their algorithm, they just count the number of times the loops execute. But in this case, you need to be cautious because the situation might get tricky sometimes, especially with nested loops. We're going to see an example later on about this. And also you will see that the method becomes a little bit much simpler when we introduce the big O notation. To illustrate what we have just explained, let's apply it on an example. So the example we consider here is the example we started with. It's about summing the elements of an array A of size n. This is the algorithm. So we're going to be counting just the relevant operations. And the relevant operation here is the sum, because you're going to be adding the elements, which is going to be this operation here. And if you look, we have this loop, and the loop repeats n times. So the complexity is going to be what? It's going to be just fn equal n. So given an array of size n, we need n additions. Now what you can do also is to go a little bit more thorough and more accurate on computing and count all the operations. And you're going to be finding something which is close to this number here, 5n plus 4. How did we do that? Well, you have to count, for example, this one here. This is one operation. In the loop, we have this initialization, which is going to be executed just one time. This condition here is going to be checked n plus 1 time. So it's going to be n time for all the elements, for all the values of I, and then at the end we need to add another one. And plus this operation here is going to be executed n times. Sorry for the writing. Here, if we want to be precise, accessing the array is one operation. Doing the addition is another operation. And doing the assignment here is another operation. But these operations here are going to be executed n times, so you have to multiply by, sorry, here it was 1. So you have to multiply by n. And if you do the math here, you add all these quantities, this one, plus this one here, plus this one, you will get something which is close to 5n plus 4. If you miss it by 1 or 2, it's not a big deal. So it's just an approximation. Now let's look to another example where we have embedded loops. And this problem is about adding the elements of a square matrix n by n. So it's the same problem. We need just to add the elements of the matrix. And for this, we use two loops. One is embedded in the other one. The first loop allows us to go through the rows. And for each row, we go through the columns. And if you count just the number of additions you're going to do, which is this addition here, well, the number is going to be just like the complexity is going to be n squared. Why? Because the external loop, this one here, repeats n times. And each time this external loop repeats, the internal loop repeats n times. So at the end, how many times do we execute this one? Well, it's going to be n squared. And actually, it's the number of the elements in the array, because you're going to need to go through all the elements here. We have n square elements, so the complexity is going to be n squared. And the same as we did previously, if you want to go more precise, well, you can compute all or count all the number of operations. Here we have 1. Here we have this initialization is 1. Here this condition is n plus 1. This incrementation is n. And then if you go to the embedded loop, well, this operation here is going to be executed one time, plus n plus 1 plus n. But the whole thing is going to be repeated n times, so we have to multiply by n. And this operation here is going to be executed n squared times. For the access to the matrix, plus n squared additions, so you need to add n squared for the additions, and n squared assignments. So if you count all of these things, you should get something close to this one. Another example to cover other cases of embedded loops is the case of summing the elements of an upper triangular matrix of size n by n. So in this matrix, we have the elements down the diagonal are all zeros, so it is an upper diagonal matrix. To sum all the elements, we do it this way. So we go through all the rows here with this loop. So I will start from 0. It goes up to n. So here we start from 0 up to n. Actually, we go up to n minus 1. And for each row, we have the internal loop, which starts from I. So j starts from I each time. So when I is 0, you start from 0. When I is 1, you start from 1, because you want to start from this one. When I is 2, well, you start from 2 here, and so forth. So here, j doesn't start from 0 as in the previous example, but it starts from I. And the complexity here is a little bit tricky to compute. If we want to do it, well, we need just to see that for the first row, we're going to be summing n elements. For the second row, we're going to be summing n minus 1 elements. For the third row, we're going to be summing n minus 2, etc. And the last row, we're going to be summing 1 element here. So the complexity is going to be what? It's going to be something like this. Fn is going to be n plus n minus 1, n minus 2, etc. up to 1. And this quantity here is equal to this, which is equal to this. And so the complexity is going to be n squared over 2 plus n over 2. For the more detailed complexity, where we count all the operations, I leave it as an exercise. Now for this here, this sum, to see how we get this number here, well, it's quite simple to do that. So we just need to write that s equals n plus n minus 1 plus n minus 2, etc. up to 1. Then you need just to write it one more time. S is equal, but you write it in the reverse order. You put 1 plus 2 plus 3 plus up to n. And then you add the whole thing here. So if you add these two here, you get 2s equal. And then you have 1 plus n here, which is going to be equal to n plus 1 plus these two here, n minus 1 plus 2 equals n plus 1. And this one is going to be also giving you n plus 1. And also the last one is going to be n plus 1. So if we add all these things, how many n plus 1 do we have? We have n. So 2s is equal to, sorry for the writing, n times n plus 1. And therefore s, the sum we're looking for, is going to be n plus n times, this is times n plus 1 over 2. And this is the quantity. So far, the complexity of all the problems we have seen depended only on the size of the input. So all inputs of the same size had the same complexity. We talk about one case scenario, and people talk in general about the worst case scenario too. And often with other problems, the complexity for inputs of the same size is not always the same. So even if the inputs have the same size, for some inputs the complexity is less than other inputs. And we talk in general about three possible cases. We have the best case complexity, we have the worst case complexity, and also the average case complexity. The best case complexity is the complexity of the case which requires the minimum number of operations. The worst case complexity is the complexity for the case which requires the maximum number of operations. And the average case complexity is the average of all possible complexities. This complex average case complexity sometimes is complicated to compute. Why? Because you need to know the probability distribution of your input. In the next slide, we're going to be illustrating this with an example. This example here is about searching. So given an array A of n elements, we're going to be looking for the position of element X. The algorithm is this one, and what the algorithm does, given X, we're going to be going through all the elements of the array here. We compare each element with the value of X, and if we find a match, we return the position and we get out. Otherwise, if there is no match and we come here and we return -1. -1 means that we didn't find the element. Now, if we analyze the complexity of this algorithm, you will see that the complexity depends on not only on the size of n, well, it depends also on the value x, or the input parameter x here. For instance, if you give me value 12, x is equal to 12, what I'm going to do is just to compare it with the first one, and we'll find it and we return position 0. But if you give me, for example, value x equal 11, well, I'm going to be comparing with the first one. It doesn't match, the second one, the third one, etc., up to the last one. So I have to go through all the elements, and the number of comparisons is going to be n. So we have different complexities depending on the value of x. If you give me, for example, 17, the number of operations is going to be what? 1, 2, 3, 4, and 5 operations, etc. So it depends on the input. So in general, we have three cases. We have the best case scenario. The best case scenario happens when x is equal to 12 here, and we just do one comparison. So the best case complexity is 1, only 1. The worst case scenario happens if the value of x happens at the end of the array. We're looking, for example, for 11. Or if we're looking for a value which is not in the array. In this case, you need to go through all the elements, and you're going to be performing n comparisons. And the average case scenario is the average of all possibilities. And this is a little bit tricky to compute because you need to know what is the probability distribution of your input. Now, if we assume that we're going to be looking only for the values which are in the array, so we're going to be looking just for 12, 45, 32, up to 11, we're not going to be looking for anything else. Well, in this case, if we assume also that the probability of occurrence of each one of these values is equally likely to happen, means it's like kind of a uniform distribution. So it's going to be, the probability is going to be 1 over n for each one of them. Now, to compute the complexity, the average complexity is going to be what? It's going to be the complexity for each one times the probability of occurrence of each one. So the complexity of value 12 is going to be 1 times the probability of the occurrence of 12 is going to be 1 over n, plus the complexity of 45, which is 2, multiplied by 1 over n, etc. And the complexity of last value is 11. It's going to be n operations. The probability is 1 over n. And this is equal just to 1 plus 2 plus, etc. up to n divided by n. And this would give you something which is roughly equal to n over 2. This is the average complexity. Now, we have a question here. In general, we focus more on the worst case scenario. Let me just delete these things here. So in general, we focus more on the worst case scenario. Why? If, for instance, I ask you to write an algorithm, imagine that this algorithm is going to be used in a nuclear power plant to, for example, control the cooling system of the nuclear power plant. And this algorithm will take, let's say, for example, a fraction of a second most of the time, but there is one case where it takes 2 hours. The problem is that if you implement this algorithm and this worst case scenario happens and the station heats up, so if you try to launch the cooling system, it's going to take 2 hours, and then you can imagine what's going to happen. So it's going to be a catastrophe. So this is why people in general compute the worst case scenario of an algorithm. Even if sometimes, for some specific problems, people look for the average case scenario. They want to know what's going to be the complexity for the average scenario. That's it for the first part of this lecture. In this part, we learned why the study of complexity is important, and also we learned to estimate the time complexity of an algorithm. In the second part, we're going to be learning about the remaining points. First, to determine the complexity class of an algorithm using the big O notation, then compare the complexity of different algorithms and select the best one eventually. And the last thing is learning about the big omega, the big theta notation, and how they are related to the big O notation and when to use each one of them. That's it for now. I hope you enjoyed this lecture, and see you in the second part.